Hi, I'm Josh, and this is Electronics Unscripted, where we take an intuitive and unscripted approach to DIY electronics. Today I wanted to do a quick video about analog to digital conversion. I'm using something called an R-2R resistor ladder. This resistor ladder is cleverly crafted to convert a binary input, in this case 8 binary bits, into an analog output. The basics of this voltage ladder are that you have these self-similar resistor dividers that split the voltage at half at every step of the way. And you have 8 individual inputs. So you can't see me touching my screen. You have 8 individual inputs into the ladder, and then it's tied to ground over here, and then your output is here. And we'll see the physical packaging of this particular chip matches this almost identically. Now the idea with these inputs is that there's 8 of them, so those map to a digital 8-bit input, right? And you either tie those to a logical 1 or a logical 0. So they're all tied to ground right now, and the output of this circuit is 0 volts. But you can toggle each one of them up to the Vref, which is the voltage reference. And in this case, that's 3.3 volts. But what happens is whenever you toggle one of these lines to 3 volts, this voltage network for every step of the way divides that voltage by half every step to the left it takes. So if we turn this one on, you can see that voltage was divided in half. So that step divides a voltage in half. This gets divided in half and then in half again. That 0.825 is 1/4 of our Vref of 3.3 volts. On down the line, every single one of these 3.3 volt inputs gets divided in half every step along the way it does. And that exactly maps to binary, where the most significant digit is worth twice as much as the next one, is worth twice as much as the next one, and so forth and so on. So now let's turn all of these on, and the effect is additive. So each one of these things contributes their 1/8 or 1/2 or 1/16 and so forth to the voltage total. So as we toggle these on, we'll see the output voltage goes higher. So now that we toggle them all on, we see that we have 3.287, which is a little weird. That's not 3.3 volts, but remember, this is a digital approximation. It's a half plus an eighth and plus so forth and so on. So if you were to be able to expand this network out to infinity, you would eventually be able to reach 3.3 volts. But we have some quantization here because we've only got 8 levels. We get effectively 3.3 divided by a half plus 3.3 divided by a quarter, so forth and so on, all the way down to 3.3 divided by 1/28, which is a really small voltage. And the summation is indeed 3.28, which is what we see here. Let's switch over to an actual real-world implementation of this, and I'm going to show you the voltage ladder that I bought on DigiKey. So this is a Bournes voltage ladder. Pin 1 is here. That's meant to be tied to ground. The next 8 pins are the digital inputs. And the last pin over here is the digital output. Down here, I've wired this to my Raspberry Pi Pico. I've got some dip switches that control the digital inputs into here. Now, originally I wanted to wire these dip switches directly to the voltage ladder, but with a dip switch, you either have to have a pull up to the Vref or a pull down to ground. That messes with the resistor network. So those resistors that you have to use for a pull up or a pull down mess around with those voltages, and basically it doesn't work right. It kind of worked, but it didn't work properly. This is a really, really glorified on-off switch. Basically all the Raspberry Pi Pico is doing is reading these digital inputs and producing a proper Vref of 3.3 volts or ground on the 8 pins in the middle of this chip here. You can see right now I've got all the dip switches turned off, and I've got wired up this cute little AliExpress voltage meter. One of the interesting things about these voltage ladders is because it's composed of 10 and 20K resistors, you need a relatively high impedance to read out from this chip. You can't really draw any amount of current from it, or you will bias the resistor network and change the DAC output. What I've got wired up right here is an op amp wired in a 0 gain voltage follower configuration. So this is just serving as a buffer so that I can plug my little display into the op amp output without biasing this resistor network. Let's go ahead and play around with this. Remember, in the simulation, when we toggled this most significant bit here to 1, we got half of the VREF. So let's see what we get here. We get 1.63, which is pretty close. I think we had 1.68. I wouldn't expect the real world circuit to be quite as good as this, but now as we go down, we should get, again, that's roughly half. So we're seeing every step of the way, this real world voltage divider is dividing each level by half, by half, by half. So here we have 3 halves, or 1/8. So this 0.4 is 1/8 of the 3.3 volts, which is about right. 8 times 0.4 is 3.2, which is close to our VREF. If we turn everything on here, we get the 3.28 voltage. Now remember, this was not, it's not going to give us the full VREF, that full 3.3 volts, because we're have some quantization errors here. We're digitally approximating it with a half plus a quarter plus an eighth plus a 16th and so forth and so on. So what can I do with this? I mean, obviously I can sit here and toggle bits and kind of demonstrate the principles of how this voltage divider works, but this is slow. The obvious target here is that I want to toggle these at microcontroller speed. So in the audio frequency space, so maybe I could use this to generate audio waveforms. So this will give me 8-bit audio. I can generate arbitrary audio waveforms by hitting arbitrary voltage levels here. And that'll probably be the next video where we're just doing a simple audio out. But then beyond that, what I want to do is I want to create an arbitrary function generator in the megahertz level. So if I use programmable I/O on the Raspberry Pi Pico, I can get sample rates, so sample being the number of times I output a digital value. So in order to generate an accurate waveform, you might need about 64 samples per waveform of a, say, for example, a sine wave, something like that. Maybe a little less, but you know, we don't want to go much below 64 or 32 samples per waveform because things get very, very jaggedy. If I'm doing 64 samples per waveform at the native frequency of programmable I/O, I can hit maybe 1, maybe 2 megahertz actual function outputs. So I can generate arbitrary waveforms at 1 to 2 megahertz. That's my target for this eventually. I want to wrap this up probably in a self-contained box, and I might even think about making a PCB for it eventually so that I can just have my cheap little function generator. Well, thanks for watching until the end. This has been Electronics Unscripted.